Happy Pi Day, space fans. 3.14159 and counting. Yes, it's March 14th. And if that sounds like an excuse to talk about an exoplanet with a 3.14-day year, that's because it absolutely is.
But before we get to our Cosmic Pi celebration, we have a packed episode. A story about where our own sun came from, a big announcement about where China's astronauts might first set foot on the moon, and Russia's bold plan to pick up where the Soviet Union left off at Venus.
Plus, a nuclear-powered flying drone for Saturn's moon Titan is now actually being built, and China's race to beat everyone to a Martian soil sample is well and truly underway.
I'm Avery.
And I'm Anna. This is Astronomy Daily, Season 5, Episode 63. Let's get into it.
Here's a question that sounds simple, but turns out to be surprisingly deep. How did our own sun end up where it is in the Milky Way?
Right. I mean, you might assume it just formed where it is, but the evidence has been pointing somewhere else for a while. And a new study published this week in Astronomy and Astrophysics might finally have the answer, and it involves thousands of stars traveling together.
Researchers at Tokyo Metropolitan University and the National Astronomical Observatory of Japan built the largest ever catalog of what are called solar twins. Stars so similar to our sun in temperature, mass, chemical composition, and surface gravity that they're essentially its cousins.
They compiled 6,594 solar twins, which is a staggering number when you think about how special we tend to think our sun is.
And they used ESA's Gaia satellite data to determine two things about each star: how old it is and where it has been moving. What they found was a striking pattern. A large number of these solar twins are between 4 and 6 billion years old, which is the same age bracket as our own sun.
That clustering is not random. It suggests that the sun and many of these stars formed in the same general region of the galaxy, probably closer to the Milky Way's inner regions, and then gradually drifted outward together over billions of years.
But here's the puzzle that the researchers had to solve. The Milky Way has what's called a galactic bar, a rotating bar-shaped structure of stars and gas near the center. That bar creates something astronomers call a co-rotation barrier, which basically traps stars in certain orbital zones and makes it very hard for them to move outward.
So how did the sun escape?
The theory is that when the sun and its companions formed, the galactic bar was still in the process of forming. It wasn't fully developed yet. And the weaker barrier may have allowed whole groups of stars to break out together, carried along by the dynamics of the early galaxy.
And the implications of this go beyond just knowing our sun's origin story. If the sun formed much closer to the center, researchers estimate about 10,000 light-years closer than it is today, then this migration may actually be part of the reason Earth became habitable.
The galactic center is a harsher place. Higher star density, more frequent supernova explosions, more high-energy radiation. Moving outward placed us in a calmer neighborhood, one where complex chemistry and life could hold and persist over billions of years.
So our sun didn't travel alone. It was part of a wave, a kind of ancient stellar migration. And that journey may be one of the reasons we're here to talk about it.
There's a lot to be grateful for in that story.
If you've been following the global moon race, you'll know that China has an ambitious target to land astronauts on the lunar surface by 2030. And this week, we got the clearest picture yet of where that landing might happen.
A new study published in Nature Astronomy has highlighted a region called Rimai Bode, a volcanic area near the lunar equator on the moon's near side, as the leading candidate for China's first crewed lunar mission.
And the description that researcher Jun Huang from the China University of Geosciences used for it is just perfect. He called it a geological museum.
Because within a relatively compact area, Rimei Bode contains 5 distinct terrain types: ancient pyroclastic deposits from volcanic eruptions, smooth mare basalts, 2 different rill systems which are essentially long channels or cracks in the surface, and nearby highland material. 5 completely different chapters of lunar history, all accessible from one landing zone.
That's the key point for mission planners. A scientifically rich site is only useful if it's also safe and practical. And what makes Rimae Bode attractive is that astronauts could potentially traverse across several very different geological environments without having to travel enormous and risky distances.
The researchers dated some of the earliest volcanic activity in the region to roughly 3.2 to 3.7 billion years ago. That's deep lunar history, and those ancient pyroclastic materials could include ash and glass beads thrown up from the moon's interior, which would be completely different from the rocks returned by the Apollo missions or China's own robotic Chang'e missions.
This site didn't come out of nowhere. Chinese researchers had originally screened 106 potential landing areas and narrowed them to 14 candidates based on practical requirements: near-side location for communication with Earth, access to solar power, and terrain safe enough for landing and surface operations.
From that shortlist, the new paper proposes 4 specific landing spots within Rimae Bode itself, each offering slightly different scientific priorities while still meeting those safety criteria. The plan also includes the use of an unpressurized rover to travel between geological units, which would dramatically extend the science possible in a single mission.
China's crewed lunar program is part of a larger sequence that includes Chang'e 7 and Chang'e 8 missions, with long-term goals around a South Polar research station. But Rimae Bode as a first landing site makes a lot of sense. Near side for communications, scientifically diverse, and a manageable operating environment.
It's still a candidate rather than a confirmed destination, but this is the most specific and scientifically detailed case we've seen yet for where China's first astronauts might set foot on another world.
Another country making a big announcement this week. Russia has announced plans to launch a mission called Venera D to Venus in 2036, and it's an ambitious one. We're talking about a lander, a balloon that would float through the Venusian atmosphere, and an orbiter, all working together.
And the historical context here is remarkable. The Soviet Union is the only nation in history to have successfully landed and operated spacecraft on the surface of Venus. Venera 7 did it first, back in 1970, and over the following 13 years, the Soviets sent a whole series of Venera landers and orbiters, 16 missions in total across 22 years.
And when you understand what the surface of Venus is actually like, that achievement becomes even more extraordinary. Surface temperatures around 900 degrees Fahrenheit. That's 480 Celsius. Atmospheric pressure more than 90 times that of Earth at sea level. It is a genuinely hellish environment.
The Soviet Venera landers didn't just survive, they sent back images. Those photographs of Venus's volcanic rock surface, tinged yellow by the sulfuric acid clouds above, remain some of the most extraordinary images in the history of space exploration.
Russia hasn't been to Venus since 1983, and Venera D has actually been in planning since 2003. It was at one point even under consideration as a joint mission with NASA, before Russia's 2022 invasion of Ukraine ended that kind of collaboration.
Russia's first deputy prime minister Denis Manturov confirmed the mission this week, describing Venus alongside the moon as central to Russia's space ambitions. And one of Venera D's key scientific goals will be searching for signs of microbial life in Venus's clouds.
That's not as outlandish as it might sound. The cloud layers of Venus, at altitudes of around 48 to 60 kilometers, have temperatures and pressures not unlike those at Earth's surface, and there have been disputed detections of phosphine and ammonia there, both of which could potentially be biological in origin.
Russia isn't the only nation looking at Venus right now. ESA's Envision mission, India's Shukrayaan-1, and NASA's Da Vinci and Veritas projects are all in various stages of development. Venus is having a moment.
And if Venera D launches in 2036 as planned, it would extend one of the most impressive and now largely forgotten legacies in space exploration history. The Soviets conquered Venus. Russia wants to go back.
Now, here's a milestone that deserves a moment of appreciation. This week, engineers at the Johns Hopkins Applied Physics Laboratory in Maryland officially began assembling NASA's Dragonfly rotorcraft, the nuclear-powered drone that will one day fly across the surface of Saturn's moon Titan.
This is the point where a mission stops being a plan and starts being a physical thing. Principal investigator Elizabeth Turtle put it perfectly when she said, "This milestone essentially marks the birth of our flight system."
So what is Dragonfly exactly? It's a car-sized 8-rotor drone. Think of a very large quadcopter, but with 8 rotors and 4 counter-rotating pairs. It'll be powered not by solar energy, but by a radioisotope thermoelectric generator, a nuclear power source, because sunlight on Titan is too faint and too inconsistent to be useful.
And Titan is just a spectacular target. It's Saturn's largest moon, and it's unlike anywhere else we've thought about sending a mission. It has a thick nitrogen atmosphere, denser than Earth's, which is actually what makes flying there possible. It has rivers and lakes, but not of water, of liquid methane and ethane. It has complex organic chemistry raining down from the atmosphere like a slow chemical snow.
Scientists think Titan's surface chemistry might resemble what Earth looked like before life emerged, which is exactly why it's so exciting from an astrobiology perspective. Dragonfly will fly to dozens of locations across the surface, stopping to collect and analyze samples as it goes.
The first power and functional tests have already been completed on Dragonfly's integrated electronics module, its brain, and its power switching units. The aeroshell and cruise stage are being assembled at Lockheed Martin in Colorado, and the wind tunnel testing at NASA Langley has already validated the rotor design.
The timeline? Integration and testing continues at Johns Hopkins through this year and into early 2027. Then system-level testing at Lockheed Martin. Then final environmental testing back at Hopkins before heading to Kennedy Space Center in spring of 2028 for launch on a SpaceX Falcon Heavy that summer.
Arrival at Titan, 2034. And once there, Dragonfly aims to cover more than 108 miles of terrain, nearly double the total distance traveled by all Mars rovers combined. It is one of the most audacious planetary missions ever conceived. And this week, it became a real spacecraft.
More news from China. The race to return samples from Mars is very much on. And this week came confirmation that China's entry in that race is moving from engineering prototypes to real flight hardware.
Chief designer Liu Jicheng announced at China's annual Two Sessions political meetings on March 12th that Tianwen-3 has achieved breakthroughs in all key technologies and now is entering the flight model development phase, meaning they're building the actual spacecraft that will go to Mars.
Tianwen-3 is an enormously complex mission. It involves 2 separate launches from Earth in late 2028 using Long March 5 rockets, the same type that launched China's previous Mars mission and its lunar sample return. One launch carries a lander and ascent vehicle, the other carries an orbiter and Earth return spacecraft.
The lander touches down on Mars, collects at least 500 grams of Martian rock and soil using a combination of a scoop, a drill, and a small drone. Then the ascent vehicle launches those samples into Mars orbit. There, it rendezvous with the orbiter, which then carries the samples all the way back to Earth, targeted arrival in 2031.
If successful, that would make Tianwen-3 the first ever mission to return samples from Mars. And that's important context. NASA's own Mars sample return program was effectively canceled earlier this year when it received no funding in the 2026 appropriations bill.
China has narrowed its landing site candidates from 106 down to 19, with the final 3 to be selected by the end of this year. Candidate sites include ancient shorelines, clay mineral-rich terrain that could preserve organic molecules, and areas associated with Mars's ancient water systems.
The primary scientific goal is the search for biosignatures, potential signs that life once existed on Mars. The mission is also open to international collaboration, with China inviting partner payloads and promising international scientists access to the returned samples.
This is a story worth watching very closely. By the time Tianwen-3 launches in 2028, it may well be the only active Mars sample return mission on the books. The first Martian soil in a laboratory on Earth could be arriving on a Chinese spacecraft.
We'll keep an eye on this one. The geopolitical ramifications, not to mention bragging rights, could be quite important.
All right, we saved the best for Pi Day. And NASA's Astronomy Picture of the Day team clearly agrees with us because today's APOD is dedicated entirely to K2315b, the exoplanet with a year that lasts almost exactly 3.14 days.
K2315b was discovered using data from the Kepler Space Telescope's extended K2 mission and announced back in 2020. It's an Earth-sized world orbiting a cool red dwarf star, an M-type star, about 185 light-years away from us.
Now, an orbital period of 3.14 days means it is very close to its star, very close, which means its surface temperature is absolutely scorching, the kind of baking hot that makes any thoughts of habitability evaporate immediately.
But that's fine. K2315b is not here to be habitable, it's here to be delightful. Because of all the exoplanets we found, and we found thousands now, this one just happens to orbit its star in almost precisely pi days.
The precision is genuinely striking. Astronomers measured the orbital period at 3.14159 days, which, if you've had your pi memorized since school, you'll recognize as pi to 5 decimal places.
The universe didn't do that on purpose, obviously, but it's a beautiful coincidence and a wonderful reminder that the cosmos doesn't always have to be profound and weighty. Sometimes it just gives you a planet that celebrates mathematics.
So, from all of us here at Astronomy Daily, happy Pi Day. May your circles be perfect and your exoplanets be numerically satisfying.
And that wraps up episode 63 of Astronomy Daily Season 5. What a show today! Solar twin migrations, China's lunar museum, Soviet-era Venus nostalgia, nuclear drones for Titan, the Mars sample race, and the Pi Day cosmic treat.
If you enjoyed today's episode, please leave us a review wherever you listen. It genuinely makes a difference in helping new listeners find us, and share the show with anyone who needs a little more space in their life.
You can find us at astronomydaily.io, and we're at Astro Daily Pod on X, Instagram, TikTok, YouTube, Facebook, and Tumblr. All your show notes, links, and extras are on the website.
We'll be back on Monday with more of the universe's greatest hits. Until then, keep looking up.